There was an extension on the corrections to Friday. I'll be collecting those at the start of the hour on Friday. Again, all the other things hold true, the format and stapling. Please staple. Here's the answer to any questions like this. No, I don't have a staple. No, I don't. And I won't then either. Okay.
Do you have a stapler?
Yes, just no staples. No, I do have a staple. I have like these sweet ones I stole from IBM when I left there.
Technically acquired.
Acquired, yes,
Technically acquired.
Technically acquired.
Good term. Just appeared. You don't see
They
it.
are solid. It did just appear. Man, they are like, they weigh like 20 pounds each. They're like made of. Okay, I saw you walking the other way, and I was like, David.
Oh, so much.
Okay, all right. Glad to see you. Let's just, right up front, Monday is going to be a work day. And we're going to need, just like we needed whatever happened on Monday to be a work day, next Monday is going to need to be a work day because there's a new web workup soon. Within, I don't know, sometime before the end of the hour, it'll open up. Got a little fuse on it. So it's web work next, whatever next is. Last plus one. And there's a lot of stuff going on in this that will be kind of reawakening ancient synapses, ancient mathematical synapsi, or whatever the plural of that is. And let me kind of give you the heads up on what we're going to do. So here's the lead in. Let's say I had y equals 1 over x squared. And that function looks like this. And then there's like, ooh, that is terrible, because this is symmetric and beautiful, and that's a little better. But what if I was interested in finding this area? So now, I want you to think about this, because it's a little intense. That never ends, right? That never ends. That goes on forever. This is asymptotic. So, an unbounded region. And I'm asking, does it have a finite area? I was just thinking about you.
Sorry.
It's okay, I'm glad you're here. It's okay. I was just like thinking, I was like, Kelby, where's Kelby?
Sorry.
It's okay, no, it's great, you're here. You don't owe me a single apology. Even if you don't come, you don't owe me an apology.
Okay.
I just take it very personally. So, finite area is the question. So it seems really strange to have an unbounded region, but still have a finite area. So this is like one of my favorite things to talk about. It's quite amazing and beautiful. And the answer is sometimes and sometimes not. Depends on the function, depends on where we're integrating, and so forth. So if I was going to find that area, let's just do this intuitive. Let's see, this is 1 here. Yeah. And of course, this is 1 over x squared. So I'm going to integrate from 1 to infinity. So now we get to use that. And that's fun and beautiful because of infinity. Yes! Stop it. Stop it. 1 over x squared dx. Even if, like, does it make sense that that would be the expression for the area? You know, because that's just, like, integrals are all about area, right? But now we've got this quite amazing thing on top. Well, here's what we're actually going to do. Here's the plan for anytime we have an infinite limit, what we're going to do is first replace it with a finite limit. So the first thing I'm going to do is find the integral from 1 to b. And I'm going to literally leave b as a variable. And I've got 1 over x squared dx. So first find this. Then take the limit of that answer as b goes to infinity. So this is equals to. So check it out. You replace your infinity in the integral, the trouble spot, with a variable. Do it just like this. That's all chill. Cassie probably thinks that's chill. And then do this. And then we take the limit. So we'll crank out this formula and then do that. Let's go ahead and do that. So this is the limit as b goes to infinity. So this is actually x to the negative second, right? So I'd use the power rule, and then I divide by the new exponent, which is just a negative, and then I go from 1 to b. Let me stop, bless you. Oh, you are masked, that's lovely. Are you feeling bad?
A little bit.
Oh no, I'm sorry.
It's okay.
I hope you stay. I know you got, I don't need to tell you. You've got a lot of stuff going on, you know that. You get sick, let me know, we'll figure something out, okay? Is everybody okay with this? Yeah. So now, work this part out. So this is equal to the limit as b goes to infinity of, and I'm going to use bracket, negative b to the negative first minus negative 1. That's what that would turn into, like so. Simplify. I'm going to rewrite this as a fraction again, because it's so much easier to do these infinite limits in fractional form. Do you remember back in Calc 1, the old L'Hopital's rule? That was all about fractions, and it was all about limits at infinity for the most part, or infinite limits, which aren't the same. But we'll talk about that when we get there. This is a limit at infinity, because we're literally claiming we can get there. And so then this is negative 1 over b plus 1. What happens to this as b becomes larger and larger? Gets smaller and smaller, right? So the top is fixed at 1, and the bottom is getting bigger and bigger. So imagine 1 over 10, 1 over 1,000, 1 over a billion. That quantity is getting smaller in magnitude each time. So what you need to think about is that infinity isn't a place we can get. It just indicates that we never stop growing. So unbounded growth. I guess that's the growth direction for us, unbounded growth like that. So let's just get a couple rules out here. If I have limit, just a refreshers, if I have limit as x goes to infinity of a fixed quantity over literally any power of x, that's 0. Because the top stays fixed, bless you, and the bottom keeps blowing up. And help. I don't even know what happened.
This is not a human noise.
It wasn't? No. Bless you, Mr. Cowan. So this is a good rule to remember, because it's going to happen a lot. I'm just on like polite mode, like 24/7. I'm sorry, Vivian, what was that?
Can you explain that?
Yes, so the top is fixed and the bottom is just blowing up, and this works for plus or minus infinity. So for example, the way to think about this is, let's say x is 1,000, you know, and then we've got, and this thing on top is just you could think of a constant maybe. That's another possibility. So let's say I've got like 17. What the hell, I can have 1,700 on top. And right now, I've got 1,000 to the nth power. So this is a really large number right down here. So what I've got really is a fixed thing over a large thing. And this large thing is getting larger and larger. So thinking about ratios like 1,700 over 1,000, 1,700 over a million. That's 100,000, a million. If you crank this out on your calculator, you're getting a number with more and more zeros in front of it. Does that kind of make sense? Or not? Ask some more questions.
So the larger the thing in the bottom, the more closer it gets to 0?
Yeah, I know, it's painful to say, yes. Yeah, the smaller in magnitude it gets. Yeah. So great rule of thumb. to absolutely keep in mind. Let's actually talk about another rule of thumb that we might need. This rule of thumb would be if I have the limit as x goes to infinity of x to some power. Here I've got x becoming larger and larger, and I'm raising it to higher and higher powers. What do we think that is? So like, for example, what is the limit as x goes to infinity of x cubed? Take something that's getting bigger, so 1,000 cubed. I don't even know what that is. What is that, a million, a billion? 10,000 cubed, even bigger, more and more zeros. So the answer here, you might not even be certain what I'm asking about. That'd be positive infinity, so this would be infinity as well. That's a good, these are some good little rules of thumb to go, and that's true for any power of x. It just keeps blowing up. So when you see this, don't freak out and don't scorn it. Just think of it as x is getting bigger and bigger. That's all. Yes, ma'am.
So for that rule, is it just going to positive infinity?
Yes. Yeah, if we go to negative infinity, it gets a little trickier because it depends on if this is an odd or an even function. So yeah, you were sensing that properly. So like, for example, if I had this, negative 2x squared. So now this is, I pull that negative 2 out in front, and that kind of changes things. But here, x is getting bigger and bigger, so what is its square doing? Getting bigger and bigger even faster. But then I got this negative in front, so that's actually negative infinity. It flips the sign.
Doesn't make any difference.
Correct. Wait,
Wait, no, that's the question.
what, so ask the question again, Vivian.
Does it make any difference with the negative infinity and like positive?
Yeah, it kind of does. Yeah, it definitely does because, so for example, did a little scooter, as always. So let's take a look at a function like e to the x. Goes like that. So here I would say the limit as x goes to infinity, the further out right I go,
Oh, it's like the direction.
yes, it's the direction of growth.
Okay.
And then if I had limit as x goes to infinity of negative e to the x, that would be this one here. So that would be negative infinity. Does that help the pictures? Okay,
So,
awesome.
So are we just trying to like find the rate of change?
Yeah. We are trying to find, in some ways, I would think of it more as the equilibrium state. Does that make
Okay.
sense? Yeah? So I'm trying to find the long-term equilibrium state of the system. Yeah. So here I've got 1 over something that's getting larger and larger. That's going to go to 0. Plus or minus 0, nobody gives a shit. It's just 0. So this is equal to 1, because it's 0 plus 1 equals 1. So look at what I've just said. This area, this infinite area, actually is 1 unit squared total. Perfect. That's cool. That's really weird. So here we have an unbounded region, but a finite area. And that's going to happen a lot. I like the look on your face, Lou. That's good. We'll have counselors set up outside after this class. That's good. That's what I live for. To have people go, no fucking way. Are you kidding me? I don't believe it. I know you're not saying you don't believe it. But it is something unbelievable.
Don't.
Hopefully by the end of the hour, you will believe me. So, it's not always finite. It's not always a finite area. Sometimes, see how this thing is dying off? That's what's allowing it to be finite. It's dying off fast enough that I actually can have a finite area. Let me give you an example of one that's not. So let's take a look at this one. So find the area Josh, am I recording? I hope to God I'm recording.
Yes, you are.
Thank you, sir. Good. The area under the curve above the x-axis and above the x-axis on, and here's the interval, start at 1 up to infinity. So that curve looks exactly like this one. Give that pen a rest. So it looks kind of the same. It's ye olde parabola, excuse me, hyperbola. Kind of goes like this too. But this one has its other portion nestled down in the third quadrant instead. You've probably seen this, y equals 1 over x, looks like, yeah, looks like a parabola, a hyperbola. And I want the area from 1 up to infinity, so I want this area here. So I set up the integral. What I really want, so this area, damn, I have to buy my own pens or Regis. Like that's what grade school teachers have to do, right? The poor people who teach grade school have to buy things for their class. I just have to buy pens. There we go. So I want the area, or the area A, is going to be the integral from 1 to infinity of 1 over x dx. Top curve is 1 over x, bottom curve is 0. That's how we do it. So first thing I do is convert that to a definite, a finite definite integral, move the infinity part to a later part of the process. Okay. So let's forget about that. It may or may not be upsetting. What is the antiderivative of 1 over x?
Natural log.
Oh, thank you. I didn't even have to wait. I'll just slap those on just for the hell of it. Yeah, beautiful.
She also knew.
What's this?
Oh, you can say it.
And then I do that from 1 to b. So notice it's just what we've been doing so far. I just have to replace infinity with a b. And you don't have to use b. It's just like kind of the classic move, because when we write out the general integral, it looks like this. Guess what we'll use if we have to replace the bottom thing? Yeah, exactly. And sometimes you'd have to replace both, but I won't make you do that.
Will the homework make us do that?
It will not either. No, the homework is like a separate entity from me. I negotiate with it. Yeah, no, the homework won't make you do that. I had to talk with it. So we've got limit as b goes to infinity, plug in the limits, it's natural log of b. B is clearly positive eventually, no matter what b started at, it's eventually going to be positive. Minus natural log of 1. What is the natural log of 1?
0.
Oh, thank you. Thank God. We have learned some things. So this is now the limit as b goes to infinity of the natural log of b. What? How? Let's picture natural log. So it looks like this. What is happening to it? What is the limit as x goes to infinity of the natural log of x? It is getting bigger and bigger without bound. So it's plus infinity. So this, oh no, this is infinity. So that area is infinite and not finite. It's not dying off fast enough. It doesn't shrink down fast enough to actually die off and become finite. So what we say here, let's get some terminology. We say that this integral is divergent. We don't say it's equal to infinity. We say it's divergent. And divergent means not finite. How about we not settling, I'm going to be really precise here, not settling on a finite value. That's probably better language. If it turns out to be a number, we say that it is convergent. So the first integral is an example of a convergent integral. So this, the fact that this is a number, a finite value, means that this is convergent. And these are both, anytime you've got infinity involved in an integration, it is called an improper integral. An improper integral. And improper integrals either have infinite limits, like we've seen, so you've got an infinity here, or you've got a negative infinity down here, or infinity is hidden inside of it because you divide by 0, or infinity appears inside as division by 0, or an asymptote, or a vertical asymptote, which isn't always division by 0. Case in point, natural log has got a singularity at 0. This thing just, natural log of 0 isn't defined, and this is asymptotic. We go down that way. So that's the kind of stuff I'm talking about. Vertical asymptotes with things blowing up or down. Okay, that's the game. Now we need to explore the territory. Is there a question, Olivia? You were looking at that.
Can you? Okay, I don't
Yeah.
know if you explain it again.
No, it's okay. I can explain it differently.
Yeah.
What would you like that to be about?
Kind of got lost after when you started writing.
Oh my god. Okay. That's why I record. But we're going to be doing more examples, and you'll see this. I think by the end of the hour, you'll have seen it enough times that you'll be solid.
Okay.
And if not, there's the recording. I'm glad I record these days. You started writing. When you dimmed the lights. So, yeah, I think we'll get you fixed up. So I'm gonna ask you to do one right now, and this will help. And then I'll come over and talk to you. See what's up. So could you please do this one for me? Integral from 3 to infinity, of course you get the 3, of 1 over x cubed dx. What is step 1?
Substitute.
Yep, like that. Put the limit up front. There we go. What I'm about to eat is going to be super crunchy, so I apologize. It's literally called a cruncher roll.
Oh, those are so good.
Oh my god. Wait, who said, was that Kelby?
No, those are good.
Yeah, Costco, right?
But they're so expensive though.
Are they? I don't know, my wife orders them and I just got addicted to them, so. At first I was like, these are gross, and now I like eat like 5 a day.
Have two potential answers.
Oh, two potential answers, got it. Only one potential, only one answer.
Only one
Wait, let me
answer.
see what you're doing when you get two.
So I just, so
Yes. Yeah, so it's just 0 plus that number. Yeah, that's the only potential, you got it. How are we feeling about getting up to here? Thumbs up, thumbs, as long as we're in the upper half of thumbs. Where's this go?
0.
0, fixed thing over something squared that is getting bigger and bigger. That goes to 0. So that's how we'll take limits in here. We probably won't even need L'Hopital's rule, really, for the problems we're gonna look at. So I've ended up with, here, let me just use this over here. This is just 0 plus 1/18, and that is my final answer, 1/18. Yeah? Yes. Let me show you a cool rule of thumb. What we're doing here forms the basis of the last, like, third or quarter of the class. It won't be integration. What we will be working with at the end of the class are infinite sums of things. Like this, infinite sums. That's where we end. And it turns into integration in some ways. And so this is all kind of the heart of the very last part of the class. We'll do this, we'll forget about it, and come back real hard on it. So here's a fun and useful fact. Can't spell useful. The integral from 1 to infinity of 1 over x to the pth power, so that's p there, is equal to, now, let's see if I put in a 1 there. It converges if p is bigger than 1. So it's a finite value. So it's a finite value. And in fact, that finite value is 1 over p minus 1. That's the answer. But only if this limit is 1. You have to start at 1 for this to be true. Because notice over there we started at 3, and that's not the case at all. But if I had started at 1 over here, what would have happened? What if this had been 1? P here is, what's P here? Compare these two. What is P in this problem?
3.
P is 3. This is 1 over P minus 1. So it converges to 1 over P minus 1 if P is bigger than 1, and it diverges otherwise if P is less than or equal to 1. So you can eyeball stuff with that rule. Well, we could prove this, but I just feel like you probably, I'm not going to show you today because I want you to stay and come back on Friday. But we could, and it's really kind of cool. And you should, if you are a math major, I'm picturing you all in my head. I'm speaking to you. You should prove that on your own time because you want to. So, yeah, exactly. Yeah, everybody should do this once who's a math major. So for example, if I gave you this, that's the square root of x. Does that converge or diverge? Yeah, what's P? P is 1/2. So here, this is exactly, since x is 1/2, P is 1/2. By that rule, this diverges. And let me show you a little picture here, kind of what's going on. So this is 1 over x right here. That's the boundary line. This is the boundary between converge or diverge. If I end up underneath this, then I converge. If I'm above that, I'm not dying off fast enough to converge. So above that, so anything above that, so for example, right here, this would be 1 over square root of x. It's too much above it, it doesn't die off fast enough. This would be 1 over x cubed down here. Dies off faster, doesn't die off fast enough. You have a problem on the web work. I'm curious how this is going to work out because the picture looks like somebody hand drew it almost. It wasn't me. I don't take credit for it. But the way to do that problem, I didn't. The way to do that problem is to think of this boundary, 1 over x. Underneath that is converge. Above that is diverge. That's the law of the land. What about this?
Converge.
Converge, if it's bigger than 1. What does it converge to?
0, 0, 0, 0, 0, 0.
Yeah, this minus 1, right? So 0 0.1, 2, 3, 4, 5. How many? 1, 2, 3, 4, 5, 6. 1. And how do you invert something like that? So this is 1 over 100. That turns into a 1 over 100. That's 100, right? So this actually is 1, 1, 2, 3, 4, 5, 6, 7. Pretty big, but finite. What happens if I start inserting more zeros?
More zeros.
More zeros over here, but that's finite. That's cool. That's okay. It's just a shitload of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a big ass number. 10 trillion? What's this number? It's a 1 with 100 zeros behind it.
Isn't it a Google?
It is a Google. 100 zeros. This is a Google. Not spelled like the evil tyrant company. When you have to claim you're not evil, people should be sus. This is a Google. There isn't this many particles in the universe. Yes?
So are all the problems we're going to be doing be 1 over something, or is it just going to be just like a regular number?
What a great question. Let me segue in just a second after I finish my little diatribe here. So that's a one, so like literally this, as far as we know, there aren't this many molecules in the known universe. There's this number. This is a Googleplex. That is a 1 followed by a Google number of zeros. You couldn't write this in the entire humanities history. Like if like whatever the first human was, they started working on this, and you know you pop out, and then like they teach you how to write, and they're like, all right, little baby, get writing. And so then you're like, okay, I guess this is my life. Here I go. Keep on going. It wouldn't be done. We wouldn't even be close. Poor little baby.
It's like if you like give a chipmunk or like a chimpanzee a typewriter, eventually it'll type out like the Bible or something.
Yeah, the complete works of Shakespeare.
Yeah.
Yeah.
Is that gonna be on the web work or?
Yes. In fact, yeah. You better get started. Get going. Yeah.
Wait till you hear about Graham's number.
Oh, I know that.
Yeah.
That's 10 to the 10 to the 34th.
Yeah.
Yeah. Let's not talk about why, but yeah. I know about good old Graham. Let's look at a slightly different problem. That's a square root at the bottom. So there's no infinity in the limits, but where's the infinity? It's inside, right? Because if I plug this limit in, this limit does not exist. This thing doesn't exist at 0. In fact, if I sketch out 1 over square root of x, it still looks like every freaking curve I've drawn today. It looks like this. Doesn't have a nice negative side because x has to be positive for this to work. But what I'm finding now is this area here. Here's 1. And they all have this perfect little point there. That tip of that cusp is always at 1, 1 for these 1 over x to the p curves. So let's do this. What would this be? Well, this is a trouble spot. So I hinted that we would be replacing a trouble spot. So I'm going to replace trouble spot with a letter. So let's just make a little note. Note the integrand blows up at x equals 0. And so that makes this improper because I have an asymptote involved in the integration process. So I'm going to replace that with a, what do you think, what should my limit go to? Not infinity, 0. And we're going to be a little bit more precise. I can only approach 0 from the right-hand side. Notice this range of integration is from 0 to 1. And if I'm approaching 0, it has to be from the right. Can't even get there from the left. So we put a little 0 with a plus on it. Approach from the right. And then just do the rest. So this is x to the negative 1/2 dx. Could you please finish this for me? I know you can. The limit's at 0. You just, plug and chug. It's no big deal. That's good. You know about Graham's number. That's cool. It's a very secret number. Bring some smelling salts back here. You gonna be all right? You all right for heading If this can't wake you up too, you're super tired. I think you should get 2.
Wait. Oh,
Yes, and you did. You just gotta do your limit now.
okay.
Practice using the notation, carry it along. If you haven't taken your limit yet, copy the limit over to remind yourself, I still have to do that. Now what do we go to? So this is 2x to 1/2 from 8. Whoa, easy. Easy math, boy. It's 2. It's 2. And 1/2. When you're doing a limit that's not at infinity, just try plugging the freaking limit in. Just replace the variable with the limit and hope you're not dividing by 0. Hope for chug means not dividing by 0. If you're dividing by 0, hopefully you're 0 over 0. Use L'Hopital's rule, which we'll probably see at some point. And then step 3, if it's a fixed thing over 0, you're going to plus or minus infinity, and you might want to get a graph out. Or you do a deeper analysis. That's why we're really concerned about what side we're approaching that 0 from. Equals plus minus infinity, deeper analysis required. I sincerely doubt I will do that to you, except for the one problem I have right now. Let's see how it goes. The area is 2.
Hey, Dr. T,
Yes, sir.
for step 3, is that positive over?
That is a plus minus there. Is that what you're asking about, Josh?
Yeah, what is that? Plus over minus? Or-
Yeah, it's like, it just stands for could be positive or negative. This is
Okay.
just like to the option. It's one of the 2.
Oh, okay. That's
Yeah,
an
yeah.
arrow. I didn't know what that was below it.
Oh,
Okay.
the arrow. So this is my equals.
Okay.
Oh, this.
Yeah. I
That's
see.
just an arrow. Yes, sir. Got it. Let me make it look more arrow-like. Thanks. Always happy to be here. I know you're tired. I'm still happy to be here. Because this is freaking amazing. Any questions before I start erasing? Anything I can clarify or? Okay. Yes, Kelby?
Would we ever get a negative infinity as a divergent answer?
Possibly, yeah.
What?
Yeah, so for example, let's do one.
Oh. Actually, no, I get it now.
No. So everybody, Kelby wants to do this.
Oh, I did not mean to let that happen.
So let's do, I like it a lot. Let's do, so natural log, your favorite also. Kelby requested not only that, but natural log.
Sorry.
She sent me an email saying, we need more log stuff.
That was me.
That was you. So here's ln of x. Let's say we want to try to find this area. Is it finite or infinite or what? So you could see that if it was finite, it would be a negative area because it's underneath. Remember how that works?
Oh,
So
okay.
negative areas. That does. You're not going to stop me by saying you agree.
Well, no, but that makes
No,
sense.
no, I know.
No,
I'm
like,
just
I
kidding.
get it.
I'm just kidding. Yeah, so it could be negative like that.
Okay.
But I kind of want to do this. So what,
Okay.
what do the folks say for shits and grins? Something like that.
Shits and giggles.
Shits and giggles. Well, you got to grin while you're giggling.
I guess.
Yeah.
But what about the giggle part?
That's what I'm doing. All right. So that area would be right. Does this look good? I'm integrating the natural log function from 0 to 1. I expect the answer to be negative if it exists at all. Let's find out. Let's just actually talk about this integral for a minute. How do you do that? We just bless you.
Thank you.
How do we do that integral? What? Yeah, well, that's a derivative, definitely. We want to go the other way.
Anti-derivative?
What's that, Lou?
That actually wasn't English.
Is that Hungarian?
That was an unconfident answer. Antiderivative?
Antiderivative, love it.
I cannot remember how to get the antiderivative.
Yes.
It is.
Well, why don't we try some of the
Oh,
techniques we've learned?
Are you doing parts? Oh God, sorry guys.
So we're gonna use parts. So what I'm gonna actually gonna do some scratch work here, just so we do this. So use parts. And what are the parts? Well, this I don't know how. If I make that dv, I'm seriously confused about what parts is. Because if I make that dv, I have to integrate it again, and I'm just stuck in a loop. We're not gonna get stuck in a loop. So I'm gonna let u be the natural log. I'm gonna let dv just be the dx, 1 dx. And I'm gonna differentiate, and I'm gonna integrate, and then I'm gonna go uv minus integral v du equals x log x minus integral, look at this, v du. Pretty hot, so then that's x natural log of x minus integral of just dx equals x log x minus x. That's some good shit. So, we come over here. Let's rewrite this. So this is the limit as a goes to 0 from what side? How do we approach 0 in that region? From the right, yeah. Right. Can't even get on the left. From the right of integral a to 1 log x dx. So I'm always going to write that. I'm going to give you some stuff to write out because I want to see you do this. I won't do it today or Friday, at some point in the future. So hopefully it'll be like that trig graph quiz, right? Remember that? That never happened. That never happened. So this is limit as a goes to 0, positive, from the positive side of that quantity, evaluated from a to 1. Let's start plugging some stuff in. So that's limit as a goes to 0 from the right. Now we plug in the 1, I get 1 log 1 minus 1 minus a log a minus a. What's natural log of 1? 0. So Calby, check this out. Like right off the bat, I'm already getting some trouble here in terms of negativity. Because that part in the front is just -1. Yeah. And then this part, now when I plug in 0, I gotta be really careful because this is a mess right here. We're gonna do a little scratch work on that because you can't just plug 0 into here. Why not? Why can't I just plug 0 in?
Oh, it's an error. Right.
It is an error. I love that. That's computer talk.
Yeah.
That's an error. Yeah. Natural log of 0 does not exist, does not compute. So I can't plug 0 into here because this isn't even defined. Nice, so that's garbage. So I'll have to write it as a limit, but I can plug 0 into here, and that's okay. So this is still gonna be minus a log a, and then this piece just goes to 0 and get rid of it. The more we can shed, the better our lives will be. And that's just true like everywhere, even in math, right? Going backpacking, want a light load. Going through life, want a light load. That's why I accumulate as much garbage as I possibly can. So this is equal to -1, and I'm just gonna pull this limit up, minus limit as a goes to 0 from the right of a log a. Where's this piece go? Just the a. Where's this piece go? Got the graph. What is the natural log of something approaching 0 from the right? What is it doing? What is the graph? What was that?
Infinity?
In negative infinity, yeah, right? So as I write in this way, the graph keeps going down. So this is actually going to negative infinity right here. Oh boy. What's up, Kelby? What can I help with?
Wait, what did you just do?
Okay. So are you cool before I did that? So all I did was copy that stuff down up to here.
Yeah.
Yeah. And then I'm looking at each piece of this.
Mhm.
So as limit as a goes to 0, this piece just goes to 0, just the a part. And the natural log of a quantity approaching 0 from the right is going to negative infinity.
Okay.
Yeah?
Okay.
Okay.
It's like, what are those?
I think you're kind of like, I'm not gonna like create any more trouble. You're not creating, you're creating like amazingness. Yeah, you are. I don't care what you say. So this is like 0 times infinity. That's called an indefinite form. And the way to do this is to convert it to a fraction and then use L'Hopital's rule. Because 0 times infinity isn't 0 and it's not infinity, it can be literally any number you want it to be. Here's proof. Here's x times 7 over x. If I look at the limit as x goes to 0, that's going to 0. Let's say from the right. That's going to infinity. But really, the answer's 7. So I gotta be careful with these limits of 0 times infinity. I can put any number I want on top here, right? And this will be true. Pi, now it's pi. Now it's e. Oh my God. It can be anything I want. So this is a mess. We don't know that. So what we're gonna do is convert it to a fraction. So I'm gonna say, oop, minus lim. I hear the pens being dropped. So I'm going to bring the a underneath like this. I'm gonna leave the natural log on top. I'm gonna put a to the negative first at the bottom. So I'm dividing by 1 over a, which is multiplying by a. Now what is this doing? The top is going to negative infinity, and the bottom is going to, so the bottom's this. The bottom's going to plus infinity. That's L'Hopitalable. That's a word. It's a word in here. -1 minus limit of a goes to infinity. So I'm going to apply L'Hopital's rule. Derivative of the top is 1 over a. Derivative of the bottom is just the derivative of that a, negative a to the negative second. Can someone simplify that for me? I'm doing an awful lot of calculus. What does that fraction simplify to? Integrating's hard. It would, thank you. Yeah, it's just, and negative a, right? Because you got that negative, but yeah, beautiful. Beautiful. So this is just all simplifies to negative a. Multiply top and bottom by a squared to simplify. And and it turns out real nice. So what I have here is -1 minus limit as a goes to 0 plus of -a. What is that limit? Yeah, just plug and chug, right? Yeah, it's a 0. So yeah, it's like now you're not certain of anything anymore. No one knows what's going on, or they're doubting themselves. But this just goes to 0. Just plug. That's the plug and chug part. There's no fraction there. It's all happy. So my final answer is -1, and that's the area between the natural log curve and the x-axis in that little tiny wedge. It's actually got finite area. I actually didn't expect this to be finite, Kelby, so this is cool. I actually thought it was going to be -infinity. I haven't done this long enough. So that's shocking. That's really shocking. That sure seems like enough. Let's talk more on Friday. Some days it's just, you just like call it, right? It's like I could just go on for hours. You don't want that. I got one more thing to tell you. Hold on. Okay, sorry. This is it. But you don't have to do this. You don't even have to like do it. There's no integration. I just want to show you something. There's one other way to diverge. What if I asked you to find the area between the sine curve and the x-axis from 0 to infinity? Seems like it should be 0, right? It kind of cancels out, right? And I don't know if you remember this, but everyone I've loved calculus-wise has seen me do the area from 0 to pi, and it's 2, right? That's like the first thing I do in here, I think. So the area under that little hump is 2, -2. So I think 2 is like 0 is a brilliant guess. Yeah. But it ends up being a little more messed up than you'd think. That's cool. That was great. That was a brilliant guess. Let me just show you this. So this is hinting more toward the end of the semester, but it's good to see it now so that you'll need less counseling when the end of the semester comes. So this is actually 2 minus 2 plus 2 minus 2 plus 2 minus 2. Right? And then, good Lord, and then here's that. I'm going to do the minus plus to indicate for ad infinitum, picking up with negative first. So what could this sum be? Let's call it S. Well, what if I group these things? So let's group these two together. And this is what you were kind of doing, Cassie, and it's a pretty damn good way to look at this. Right, I can group together the first, second, third, fourth, and that all looks good. And so what is that going to be? That's 0 plus 0 plus 0 plus 0. That sure looks like 0. Right? Everything cancels. But what if I actually held off on this first one and then started grouping? So plus -2 plus 2 plus -2 plus 2 plus -2 plus 2. Now I've got 2 plus, and that adds up to what? That's disturbing, right? We should be able to like add numbers in any order and group them. We should have associativity. That's the property of associativity. Let me show you something I'll prove you at the end of the semester. And I just want to disturb you the most right now. I just want you to not be able to drive home. And I'll prove this to you. This was done by an Indian mathematician. I'll probably butcher his name, but Ramanujan.
Oh, I know who you're
Ramanujan, I've heard, I don't quite know the right way to say it, it's a Hindi name. He taught himself math and was doing all sorts of work with things like this, like just messing around with them on his own, and he sent all his work to this mathematician Hardy in the US, and Hardy looked at this stuff and was like, oh my God, this is amazing. This person taught themselves this. And one of the results that he proved is that the sum of the natural numbers is -1/12. And that seems really messed up. But the strange part is, in physics, there's a function called the zeta function. It's math in physics. There's a thing called the zeta function. I don't know how to fucking draw zeta. And the zeta function looks like this. Oops, sorry. We don't quite talk. Well, we have talked about it, but 1 over 2 z plus 1 over 3 z plus 1 over 4 z. When you look at this at -1, you get this series. And there's other expressions for this in terms of an integral, and this value is -1/12 through other means. So this person, just like messing around, came up with this and didn't even go, that doesn't seem right, and ended up being right. Powerful, profound, and crazy. So there's a movie about Ramanujan that's The Man Who Knew Infinity. I think it's a pretty terrible movie. But I have it on DVD if you want to borrow it. Let's call it. Thanks, friends. It's going to get worse. We're getting into deep waters. I'm going to have more stories.
Do you want me to stop the Dr. C?
I heard you.